Hello, this is Mrs. Mendy, and today we're going to review a little about Newton's laws. Now, I know you covered this in seventh grade, I hope, so I'm going to go through this a little bit quickly and then skip to um, parts that are a little more advanced view of it. Okay? Review Newton's first law. An object at rest will stay at rest, and an object in motion will stay in motion unless acted on by an unbalanced force. This is also known by just calling it inertia, just the tendency of stuff to stay put or to keep moving to basically continue at their same velocity. Newton's second law, you can write it in words, but it's easier to understand and faster if you just remember force equals mass times acceleration. So that is the second law, is that equation. Newton's third law, for every force there is an equal and opposite force, and it's generated at the same time. So this one is the one that is hard to understand and the one that we'll be focusing on most because the first two are pretty straightforward. This is the one that it's kind of weird and non-intuitive, so you have to work a little bit at getting to understand it. Okay, third law examples. So your foot pushes and the ground pushes back. So as you walk, if the ground was not pushing back, you would not move. So because there's nothing to push you forward. Okay. The force arrows are the same length. So if you were drawing the vectors, they're always going to be the same length. That shows that they're the same magnitude. That's really what that means, is it's the same magnitude. So the forces are the same size, but in opposite directions. Okay, so then the arrows will point in opposite directions. They can either be opposing like this, or they can be, depending on if they're a push or a pull force, they could be pulling in opposite directions instead of pushing in opposite directions. Okay, so let's see. Let's go down through there. So for these, both forces are always there, always there. So that's why I try not to say action reaction, because it's not like one happens and then the other happens. They both occur absolutely simultaneously. Okay, they always act in opposite directions, completely opposite directions. They always act on different objects. So if um, okay, I'll use this. So your foot pushes on the ground and the ground pushes on your foot. You can tell you're pushing on the ground if you leave a footprint because you're pushing into the ground. And you can tell the ground is pushing on you because you can feel it. You can feel that force. Both are real forces and can cause changes in motion. So it's hard to believe that they are both happening at the same time because we're used to thinking about motion or force as like one thing that happens. And so you have to sometimes kind of look for where the other force is. So we're going to spend some time practicing how to do that. Okay, so the third law creates these force pairs, and we'll talk about them that way. It's being a force pair. So like if you put a balloon um, and attached it to a string, blew it up, and let it go, the balloon is going to go this way, okay? But you don't think about that the balloon is pushing on the air and the air is pushing the balloon. That's actually what's happening, which is kind of weird. You just think, oh, the air is pushing the balloon forward. And it is, but the balloon is pushing on the air too. Okay, that's how it moves forward. All right. Now, this leads to the more complicated thing, the more advanced calculating thing to do. So if you've got these force pairs, okay, and they're always the same size, oh dang, the same size, I'm going to exit out of here so you can see this there without that thing on there. Okay, same size, but different direction. exactly opposite direction, okay? So that means if you've got force equals ma, F equals ma, you can do that on both sides. So if there's a force here and a force here, then there's an ma on this here, a mass times an acceleration on this side, and a mass times acceleration on the other side. So if the bat is hitting a ball with a force, the ball is hitting the bat with an equal force. It doesn't seem like it's an equal force because the ball is the one that moves farther. But that's because of different things. The ball is a smaller mass and has a different acceleration. So, okay, so if you can calculate if this equals this, then the mass of the bat times the acceleration of the bat will equal the mass of the ball times the acceleration of the ball. Okay? You're just substituting in, but this is a useful thing that you can calculate. Okay? Because if you wanted to, you might know the mass of the bat and the mass of the ball, how basically how fast you're accelerating the bat, and then you can calculate how fast or how much you're accelerating the ball. Basically, how fast it's going to go, how far it's going to go. Okay? So that we'll be practicing later. And the main magic thing to remember is that as you're going to plug stuff in, and so you'll be able to, the magic thing is remembering that ma of the one force will equal the ma of the other force. And you see how we have in the past, we've put numbers below different versions, like in acceleration, we had v1 and v2. This is kind of like this kind of terminology where you're saying the mass of the bat. So it's m sub bat is how you'd say that. Or I'd just say mass of the bat, acceleration of the bat. So it's showing you that it's the same kind of quantity, but it's for different things. Okay? We'll talk more about that later, but that's it for now.